Alright, so today we're going to take a look at free body diagrams and the practice that you guys were working on today. So we're going to start with the first scenario. The scenario is a car is being towed by a truck at a constant velocity. So as soon as I read that problem, I'm going to note the importance of constant velocity right there. And I also see that the truck exerts a force of 10 newtons. It doesn't give me a direction, but it does give me an amount. So now I'm going to draw a free body diagram. Like I said in class, I prefer dots over boxes. And I'm going to start by just drawing that 10 Newton force. Since it doesn't give me a direction, I get to choose which way I want it to go. Then there's the obvious force, as we called it in class today, Firth, the force of Earth which pulls the truck down. And I'm just going to assume that this truck is sitting on the street, so there should be a force pointing up as well. Now, the key here is that it is moving with constant velocity. As I've drawn it, this does not show constant velocity. In fact, think to yourself, which way would it be accelerating? Hopefully you said to the right, because that's where the force is. So I'm going to balance that force out by putting a 10 Newton force going to the left. For this box, I need to state whether or not it's in equilibrium. I see that all my forces are balanced, and from the problem I know that it's moving with constant velocity, so I'm going to say yes, the truck, or the car, is in equilibrium. Now I need to talk about its velocity and its acceleration. This problem made it easy, so I will say the velocity is constant and it is not accelerating. Okay. Alright, so that's the first one. Let's take a look at the next one. I have two clues here. A bird is gliding in the sky. Alone, that doesn't tell me too much, but then I also know that the bird is in equilibrium. So I'm going to draw a very artistic bird. Done. And I know that the bird is still being pulled by Earth. And so something has to be holding the bird up. And the bird is not sitting on the ground, so I'm not going to put something like street, because it's gliding in the sky. So I'm going to say air. The air is holding up the bird. Now, I didn't draw these arrows terribly well. They should look a little bit more similar, so I'm going to go ahead and erase this. Extend this arrow out to be a little bit more the same size as that one. Finally, I need to talk about the velocity and acceleration. I know that it's in equilibrium, so the bird is not accelerating. And if it's not accelerating, it is therefore moving with constant velocity. Okay, good. So next, we're given a free body diagram that shows balanced forces of a table and Earth, and then I'm giving some statements about the velocity and acceleration. So the book has a constant velocity and no acceleration. So right away, if I see no acceleration, I can say that the book is in equilibrium. And here's the fun part. So now I can write a scenario. So most of you probably would write something like, the book is at rest on the table. And that's true. This is what the free body diagram would look like. It would still be in equilibrium, and it has a constant velocity / no acceleration. But I can also make this a little bit more interesting. I could say a book slides at a constant velocity on a table. That would also work, because again, it's moving with a constant velocity, This is the free body diagram. It is in equilibrium, and there is no acceleration. So let's keep going. This one I know gave some people trouble in class, so let's talk about this dog. We have a person walking their dog holding a leash to the left. So we're going to draw a dot for the dog. The leash is going to the left, so this is the force of a leash. The dog's probably on Earth, and therefore the dog is probably standing on the ground. But we're given another piece of information. The dog is accelerating to the right. So that means there's got to be a bigger force over here. I'm going to call this the force, well, we don't know what it is. So I'm just going to leave it as an F for right now. So we have the ground, Earth, leash, and then my bigger force to the right because it's accelerating. So right away, by reading this right here, we know that the dog is not in equilibrium. Okay. Next, we're talking about a dolphin. The dolphin is not in equilibrium. So hopefully, without even reading this, you're thinking, oh, it's accelerating. And sure enough, it is. And in particular, it is accelerating down. So I'm going to start with a diagram. I'll draw the force of the Earth here. And then I'm going to assume the dolphin is in the water, so I'm going to draw a water force up. But the Earth force is bigger because it's accelerating down. So my scenario could be something like a dolphin dives into the water and speeds up as it dives. If your scenario doesn't match mine, that's fine. Okay, we have a paratrooper falling with a parachute. He is not changing speed or direction. So a paratrooper is one of those people that jumps out of planes. So we're going to draw our paratrooper. He's falling. So for sure there's the force of Earth. But he's not changing speed or direction, which means if we put those two things together, we're just talking about velocity. So if velocity is not changing, it's constant. So we've got the force of Earth down. So I'm going to put the force of, think about what would be holding him. He's attached to a parachute. So I'm going to put the force of a parachute pulling up. All right. Now we have to state whether or not it's in equilibrium. Again, we see constant velocity. We have this nice diagram here. So I'm going to say the paratrooper is in equilibrium. And finally, I would say the paratrooper has a constant velocity. So this is important and probably different from what you're used to thinking about, because the paratrooper is falling. So our gut reaction is that the force of the Earth must be bigger. Otherwise, he wouldn't be falling at all. But what we now know, because of physics, is that if your velocity is constant, even if you're falling, there has to be some other force that balances it out. So let's take a look at the last one. We're given just an equilibrium state and a free body diagram. So we see that the duck is in equilibrium, so this is a free body diagram for a duck. There's water holding the duck up. The Earth is pulling the duck down. There's a wave pushing a duck to the right and some wind holding the duck back. So all we know about this duck is that the duck is not accelerating. Because it's in equilibrium. And we know its velocity is constant. So with that in mind, we could try to write a scenario here, and similar to our book one up here, we could do two different things. I could say a duck is at rest in a pond. Being pushed by a wave. But I also could say a duck is floating at a constant velocity due to a wave. Both of those would count because, again, all we know is that it's in equilibrium and that the velocity is constant. There's no acceleration, but we don't know anything about the actual motion of the duck. And this is, again, where a lot of people get confused. So if you're watching this, I'm also going to go ahead and show you something else that will be helpful. I would encourage you to write this down elsewhere. And that is this cheat sheet right here. Okay? You can't use this on the quiz tomorrow, but it is good to know. If an object has a constant velocity, then it has zero acceleration. So my velocity is not changing, it's constant. And it's in equilibrium. If it's accelerating, it has a changing velocity, and therefore it's not in equilibrium. If it's in equilibrium, there's zero acceleration, it has a constant velocity, and can be moving, just like all the examples we just saw. And if it's not in equilibrium, it has a changing velocity and it is accelerating. Okay? So make sure you commit this to memory. Be ready for our quiz tomorrow, and I hope this helps. See y'all next time.